In this video lecture, we'll look at compensation for non-ideal circuit elements and also the gain bandwidth product. This is another extremely important and useful application of linear feedback systems. Let's start with an example issue. Transistor current gain is sensitive to both temperature and frequency. So if you plot the current gain of a transistor, the basic figure of merit for a bipolar junction transistor is beta, and beta is defined as the collector current, which you can think of as the output current of the transistor, divided by the base current, which is the input current of the transistor. And this ratio is called beta, and beta has a sensitivity to temperature, which is shown in this graph here. Beta will generally increase with temperature. And beta also has a strong dependency to operating frequency. This is some data I took from a very common and popular transistor, the 2N3904, which is this guy shown here. And this is the beta or current gain in plotted versus frequency. This is actually not decibels there, sorry about that. This is the actual value of beta. So you can see in this graph that beta is around 300, just a little bit over 300, up to about a couple 100,000 hertz. But once we get to around a megahertz or more, you can see beta falls off very quickly. And so both of these are undesirable effects. And the question is, how can we mitigate these undesirable effects? Well, the answer is feedback. So suppose we have an amplifier circuit that's made from the transistor that I just showed you on the previous slide. And this amplifier is going to provide some high gain, but of course that gain is going to vary with both temperature and frequency. So we saw in the previous slide how the gain of the transistor increases with temperature and it falls off with frequency. So our goal here is we want to stabilize the amplifier's gain. We want an amplifier that has a very predictable output one that's relatively immune to temperature, to different operating frequencies. And also, if we build a bunch of these amplifiers, every transistor we put in them is going to be slightly different depending on their individual characteristics and who manufactured the transistor, etc. So we want to try to lessen the sensitivity to all these variables. So we're going to make it, in this particular case, let's try to make it less sensitive to both temperature and frequency effects. So our method here is we're going to use passive circuit elements in a feedback loop. And the reason for this is that passive circuit elements such as resistors, capacitors, and inductors are relatively insensitive to temperature and frequency. Certainly much less sensitive than a transistor would be. So what we have here is, this is our amplifier. This is the amplifier right here without any feedback. But we're going to take the output of the amplifier and we're going to feed it back with a network which is just a simple multiplication by a factor of k. And this, again, this network here is going to be built from some passive circuit elements. For example, just resistors, and it's going to provide some multiplicative factor here. And h of j omega, again, this is the open loop gain of our amplifier without feedback at all. And this is going to have some high gain, but remember, this is going to be unstable due to temperature and frequency effects. So we know from the previous diagram, we have our standard feedback system. And so the overall frequency response is going to be Q of j omega. Notice here we're using frequency response instead of a transfer function, but it's the same function. We're just replacing S with j omega. So we have our output Y over our input X, and we've shown this system algebra several times before in the videos on this chapter. So the output is H over 1 plus K times H. Now, what we're going to do here is design K such that K is much less than 1. However, we're going to make sure that the product of K times H is still much greater than 1. So just as an example, let's say the magnitude of H, that's the amplifier's gain without any feedback. Let's say it's 1000. And let's set K, our feedback loop gain, to 100, so 0.01. And we could easily realize this multiplication K by using a voltage divider. So we have, an input voltage going in. We want the output just to be multiplied by K. So if we take these two resistors to make a voltage divider, and we have 1,000 ohms up here and 10 ohms here, well, the output is going to be this resistance, which is 10 R2, divided by R1 plus R2. So that's 10 divided by 1,010, and that is about 0.01, or about 100. So what we have now is, if we look at our transfer function again, and we just think of the magnitude of this transfer function, we have H over 1 plus K times H. So remember, H is 1,000 and K is 0.01. So multiplied together, K times H is going to be 10. So 10 is much, well, at least, pretty much bigger than 1. So we can approximate this thing as just H over K times H. So in other words, we can ignore this 1 here, since KH is 10 times bigger than it. So the nice thing here is we see that we have H on top and K times H in the bottom. And so we see that the H's cancel, and we end up with 1 over K. And this is not a surprise. We saw this in the previous video on inverse system design. This is basically the reciprocal of this transfer function here. So we went from K to 1 over K. And 1 over K, remember K is 0.01, so 1 over K is 100. So our total gain now of our amplifier has been reduced from 1,000 to 100. However, notice that this gain, at least in this simple theory that I'm showing you here, this gain is stable. It does not depend on frequency or temperature, because K doesn't. K, remember, was built with these passive resistors here. So we have traded gain for stability. This is an example of a trade-off in design, where we can have one or the other. And what we want in this case is a stable amplifier. And so this is a very commonly used technique in op-amp amplifier circuits, which we'll see later in this chapter. So let's take a look at a graph of this system here. So this is a Bode plot of our previous example here. And what it would actually look like is this. Our original gain is, we're going to call that A naught. And it's going to have a Bode plot like this, where it's going to have, over some narrow frequency range, it's going to have a relatively stable gain. But at higher frequencies, the gain is going to drop off like this, as we can see with the blue line. Now, what we have done with feedback is we have taken this gain A naught and we have lowered it down to some other value down here. A1 is the gain with feedback. But notice what we've gained. We've got a much larger bandwidth of this amplifier. The bandwidth here is much larger. We can go to higher frequencies before we start to fall off in the gain here. So this is this idea. We've traded high gain for lower gain, and as a result, we've gained more bandwidth. So this leads us to the concept of the gain bandwidth product, which we'll look at next. Let's take a look at the typical amplifier frequency response. So just some basic definitions here. A voltage amplifier is a circuit that amplifies the input voltage. So if we have an input voltage here, V sub I, we have a gain factor here, A of omega, and the output here, voltage, would just be the input multiplied by this gain A. So the magnitude of the gain of an amplifier is equal to the magnitude of the output voltage divided by the magnitude of the input voltage. It gives us the factor of amplification. Most amplifiers have a gain frequency response, A of omega, that is characterized by a single pole at the corner frequency, omega sub C. So this is the frequency response function of a typical amplifier. On the numerator, we have A naught, and that we'll see is the max gain of the amplifier. And in the denominator, we have 1 plus j omega over omega c, which is our corner frequency. So if we go ahead and take the magnitude of this function, the magnitude of the gain is equal to A naught over root 1 plus omega over omega c quantity squared. So this is plotted here in a Bode plot. So what we can see here is that the gain of the amplifier, this is in decibels, is a constant flat gain equal to A naught, which is the maximum gain of the amplifier. A naught is also sometimes called the DC gain of the amplifier. DC just referring to very low frequency. Now, the gain starts to roll off here at the corner frequency. This is omega c down here. So at the corner frequency, remember the corner frequency is defined by the 3 decibel roll off of the maximum gain here. So, and by the way, 3 decibels in gain refers to the gain being reduced to a factor of 0.707 times its original value, all right? But in decibels, that's 3 decibels. So this is the definition of our corner frequency right here. And this corner frequency also allows us to define what's called the bandwidth of the amplifier. So the bandwidth is just the working frequency range that the amplifier can work at. And we're going to assume that it can go all the way to low frequencies. Now, once we get past the corner frequency, we see the typical 20 decibels per decade fall off in gain here. All right, and this is due to this frequency response here. And we'll talk about this transition frequency down here shortly. But this is the typical Bode plot for an amplifier. This leads us to the concept of gain bandwidth product, or GBW. So this is just repeating the frequency response for our amplifier from the last page. We're going to look at the magnitude here. We're not going to deal with the phase of the gain in this course, but let's look at the magnitude here of the gain. So magnitude of A of omega is A naught. Remember, that's our maximum gain up here, divided 1 plus omega over omega c, all squared. So what we're going to do is we're going to focus on this region of the graph over here for frequencies greater than the corner frequency omega c. So for this region here, we have omega over omega c is going to be much greater than 1. So in the denominator, we can ignore that 1 because it's going to be dominated by this expression in the parentheses here. So we can simplify this. We have the square root of a square, so those cancel each other. So we end up with A naught over omega c. So let's bring this omega c, the corner frequency, let's go ahead and put that up here in the numerator. And finally, we can rewrite this thing. We can take this omega and we can multiply it over here. We can multiply both sides of this equation by omega, and we end up with this result here. The magnitude of the gain at any frequency omega, as long as we're over in this sloped region of our graph here, where omega is larger than the corner frequency, that gain times the frequency omega where we're at, all right, like just pick a place like right here, okay, that would be our omega, we could read that off the graph, we could read our gain. That's going to be equal to, all right, remember from this equation here, the maximum gain, A naught, times the corner frequency, omega sub c. This is a constant value because A naught does not change and our corner frequency does not change. So this gain times remember the corner frequency gives us the bandwidth. This is called the gain bandwidth product, or GBW. And it's a constant parameter for a given amplifier. And it's a very useful figure of merit to describe an amplifier's ability to amplify at high frequencies. So a higher gain bandwidth product is a desirable feature for an amplifier because that means we're going to have a larger bandwidth and or a larger gain for our amplifier, both of which are desirable properties. Let's work through an example that applies some of the concepts that we just learned. Suppose an amplifier spec sheet indicates a gain bandwidth product of 1 megahertz, and it tells us the DC gain is 100. So part A, let's find the amplifier's bandwidth in hertz. Part B, what will be the amplifier's gain at 1 kilohertz? And part C, what will be the amplifier's gain at 500 kilohertz? So for part A, we want to find the amplifier's bandwidth. In radians per second, which is what I showed you previously, we saw in the last slide that the gain bandwidth product is equal to A naught times omega C. And remember that the bandwidth is equal to the corner frequency. So this is radians per second. We can use this same formula and just use hertz for frequency instead of radians per second. So the gain bandwidth in hertz, which remember was given to us, 1 megahertz, is equal to A naught times the corner frequency in hertz, F sub C. So the bandwidth, which is the corner frequency, is then equal to the gain bandwidth product, or 1 megahertz, divided by the DC gain, A naught, which is 100. So this becomes 10 kilohertz. So that is our, that's the amplifier's bandwidth. So that would be shown right here in this diagram. I've constructed a Bode plot for this particular amplifier. All right, part B, what will be the amplifier's gain at 1 kilohertz? Now, since 1 kilohertz is much less than the corner frequency, remember the corner frequency is 10 kilohertz. So we're talking about something over here. We can see that this is in the flat portion of the frequency response. So our gain is just going to be equal to A naught, which is going to be 100, which is given up here. All right, part C, what about the amplifier's gain at 500 kilohertz? Well, 500 kilohertz is going to be somewhere over here. You can see I marked it on this Bode plot. It's obviously much greater than the corner frequency, which is only 10 kilohertz. So we can use our result from the previous slide. In radians per second, we have the gain at any frequency omega times omega is equal to the gain bandwidth product. So we're going to use the same formula and do it in hertz. The gain A sub F at any frequency F is equal to the gain bandwidth product in hertz. So we want to solve for the gain A sub F is equal to gain bandwidth product, which again is 1 times 10 to the 6th, or 1 megahertz, divided by the frequency we're interested in, which is 500 kilohertz, 500 times 10 to the 3rd, and this comes out to just be 2. So our gain down here would be lowered to 2. So remember, the gain up here was 100, so obviously at this high frequency, our gain has dropped off quite a bit. Another useful concept is the so-called unity gain bandwidth. And this comes directly from what we've been doing on the last couple of slides. So here's our result. Remember that the gain at any frequency, A of omega, times the frequency omega, is equal to a constant value called the gain bandwidth product. And that's our DC gain, A naught, times the corner frequency, or the bandwidth, omega C. Now, we're going to define something called the unity gain bandwidth. And unity gain just means that we set the gain to 1. So in our equation up here, A of omega, we're going to set to 1. And we're going to call omega omega sub t. All right, this is a special frequency that is associated with unity gain. And the right side of the equation, of course, doesn't change. These are constants. So A naught is still the same. And we have our same corner frequency, omega c, and these two, of course, are equal to GBW, the gain bandwidth product. So we have a new parameter here called the transition frequency, omega sub t, and it's equal to the DC gain times the corner frequency, and of course, it's also equal to the gain bandwidth product. Now, the transition frequency has several different names. It's also called the unity gain bandwidth, or you can also call it the gain bandwidth product because it's equal to that. Conceptually, it has a slightly different meaning. When we talk about unity gain, let's figure out how many decibels that would be. So remember, to figure out the decibels, we take 20 times the log of the gain. So in this case, our gain is a 1. So the log of 1 is 0. So unity gain corresponds to 0 decibels on our Bode plot. So here is our Bode plot of a typical amplifier. Remember, we have A naught is our maximum gain here, or our DC gain. Here is our corner frequency, which defines the amplifier's bandwidth. And we can see that the gain, of course, drops off after the corner frequency at 20 decibels per decade. But when we get down here to 0 decibels, we are at the transition frequency omega sub t, because that corresponds to a gain of 0 decibels. So on our graph here, we can see that the transition frequency, which is also the gain bandwidth product, is the point where our frequency response curve intercepts the horizontal axis at 0 decibels. So this sort of completes now our diagram of a Bode plot for an amplifier. We have all the characteristics shown in here that we need to know at this point. Here's an example that shows the transition frequency, FT, or unity gain bandwidth of a very common and popular transistor, the 2N3904, which is shown here. So I actually did this experiment in my lab here at home. The low frequency current gain, or beta, was measured at 320, and using my scope and a special circuit to measure beta at different frequencies, I found that the 3 decibel corner occurred at 1.25 megahertz. So from these two values, we're going to construct a Bode plot and calculate the transition frequency. So let's figure out the DC current gain first. We were given that beta naught, that's our DC gain, was measured at 320. So to convert that to decibels, we take 20 times the log of 320, which turns out to be about 50 decibels. So that is on our Bode plot. You can see it's at 50 here. So this is beta naught. And you can see that beta naught is relatively flat here. We get this, these are the actual, the black dots here are the actual data that I measured, and the red line that's fit to it is the model, what's predicted from the theory. And what you notice here is that the gain, the beta starts to fall off, and the 3 decibel point here was measured at 1.25 megahertz, and you can see then the data points follow very closely down the curve here. Now, we're asked to calculate the transition frequency. So from the last slide, omega t is equal to A naught times omega c. So in hertz, this just means that the transition frequency f sub t, the cutoff or transition frequency, is equal to beta naught, because that is our gain here. This is beta naught up here, times the corner frequency. So I have 320 times 1.25 megahertz. That gives us a transition frequency of 400 megahertz for this particular transistor. And I wasn't able to get data past about 5 megahertz with the equipment that I have, because at that point my oscilloscope starts to load down the transistor and we get bad results. But the data does fit the model very well up to about 5 megahertz. The model then, which extrapolates basically the data, you can see that comes down here. And remember, where it reaches 0 decibels, that gives us the unity gain bandwidth, or the transition frequency FT, which is 400 megahertz on this graph. Let's revisit this concept of the gain bandwidth product one more time. In the homework, you'll actually do the derivation for the following result. I'm not going to show it here, but basically a very fundamental property of the gain bandwidth product is that if we take the gain with no feedback, that's A naught, remember, or the DC gain, and multiply it by the bandwidth without any feedback, so we'll call that BW sub naught, that gives us the gain bandwidth product. But that also works for any other gain and bandwidth with feedback applied. So in other words, we're taking this amplifier that has this Bode plot shown in blue, and this is without feedback. It has a very high gain, but a relatively small bandwidth. By applying feedback, what we can do is lower the gain of the amplifier, and what we get in return is a larger bandwidth. And these two have the same product, and it will actually follow the curve just like this. And notice they both meet down here with the same gain bandwidth product or transition frequency omega t, which we just talked about. So this is just another example here of this trade-off of gain versus bandwidth, or gain versus frequency. Here's another example of the gain bandwidth product for a transistor amplifier that I built and tested here at home in my lab. This simple amplifier circuit just used a single transistor. In this case, I used an older model transistor. This 2N1305 is actually a germanium transistor, not a silicon transistor. And feedback for this amplifier is supplied from what's called an emitter resistance, R sub E. We don't have to worry about the details of all that, since this is not really an electronic circuit course. But what this does show is some of the characteristics that we've just been talking about with amplifier frequency response, and in particular the gain bandwidth product. So notice in this is a Bode plot again. This top curve here is our sort of like our control curve. There's no feedback here. So the emitter resistance was, I shouldn't say zero, I should just actually say is infinite. I removed, well, I'm sorry, it is zero. I have a short there. Okay, so we have no feedback resistance here. So as a result, you can see we have the highest gain. All right, so this is without feedback. It's something like 45 decibels. Notice that the bandwidth here of the amplifier without feedback is relatively narrow. It's somewhere around 100,000 hertz here, where we see it start to fall off. So that would be the corner frequency for that amplifier. Now I took the same amplifier, and now I increased the emitter resistance using a 10 ohm resistor instead of the short circuit that I had up here. So you can see the effect here is our gain dropped considerably. It went from about 45 decibels down to something like 36 decibels, which is quite a bit of, that's something like 9 decibels, which is quite a bit of gain loss. But notice what happens here is with the lower gain, you can see that the bandwidth is, the amplifier's gain is very flat out to a higher frequency. In fact, its corner is probably somewhere over here, or several 100,000 hertz. And then this next curve here, I increased the feedback resistance to 22 ohms. You can see the effect is to lower the gain even more to around 31 decibels. But again, we see that this thing is flat for a larger region. The bandwidth has increased. And finally, I increased the feedback resistance to 47 ohms, which lowered the gain to about 25 decibels. But this amplifier, even though it has the lowest gain, it has the highest bandwidth. It's very flat out here to around 1 megahertz. So notice how, the basic effect here is as the gain is lowered, we see an increase in bandwidth. That's because all of these amplifiers here have the same gain bandwidth product. And you can see that in the model here, which fits the data very well. The models all extrapolate down here to 0 decibels. Remember, that's where the gain bandwidth product is red, and that's around 20 megahertz. And you can see all 4 of these experiments resulted in very similar gain bandwidth products around 20 megahertz. Here's our last example with the gain bandwidth product and amplifiers. So this, one of the first op amps or amplifiers on a chip was introduced way back in 1967, and this was the famous 741 op amp. And it has a Bode plot that is shown right here. Now this is the so-called open loop or no feedback Bode plot of this op amp or operational amplifier circuit. So using this, we're going to try to answer two questions here. Part A, what is the 741's GBW? And part B, suppose that you design an amplifier with feedback such that the low frequency gain is reduced to 10. What will be the new amplifier's bandwidth? So let's answer the first question first. What is the gain bandwidth product of the 741 op amp? Well, there are two ways to do this, and we'll do them both since they sort of illustrate some different features. The easiest way is just to look at this graph and see where this frequency response plot intercepts 0 decibels, right? Because that tells us the gain bandwidth product. So we can see that the gain bandwidth product is 10 to the 6th, or 1 megahertz. Now, the other way to do it is that the gain bandwidth product is the product of A naught, which is this gain up here, times the bandwidth, which is the distance from here to the corner. So to figure out what A naught is, well, it looks like it's 100, but remember that's decibels. So 100 decibels is equal to 20 times the log of A naught. So we can divide both sides by 20. So we get 5 equals log of A naught. And to take the inverse of the log, we say that A naught is equal 10 to the 5th power, which is 100,000. So this gain up here, 100 decibels, corresponds to a gain of 100,000. So that's A naught. And then we can read on the plot here, we see that the bandwidth, which is defined by the corner frequency, or 3 decibel frequency here, is at a mere 10 hertz. So we have 100,000 times 10 gives us the same gain bandwidth product of 1 megahertz that we got from the graph directly. All right, so part B, we're going to use this op amp and we're going to add some feedback into it, and we're going to end up with an amplifier with a low frequency gain of only 10 instead of 100,000. And we want to know, what is the new amplifier's bandwidth? Well, what we can do here is, remember from the previous slide, the gain bandwidth product is equal to the A1 value, all right, which is the new feedback amplifier flat gain here, or low frequency gain, multiplied times its bandwidth, BW sub 1. So we're going to solve for BW, bandwidth, and that's equal to the gain bandwidth product, which is 10 to the 6th. That's a constant for this amplifier. And we're going to divide it by our new gain, which is 10. So 10 to the 6th divided by 10 is 100,000. So our new bandwidth is 100,000 hertz. So on the Bode plot, we can see here is the original amplifier up here in blue. Here is our new amplifier with feedback. So notice we have a much lower gain, but what we have gained is a much larger bandwidth that goes up to 100,000 hertz. So again, this is showing the trade-off in amplifier design of gain and bandwidth.